In the next couple sections, we're going to be looking at volumes and how to find the volumes of weird solids using a similar method that we use to find areas using small rectangles. So instead of looking at tiny rectangles, we're going to look at tiny 3D shapes. We're going to call these slices. So the two examples I like to start with are a stack of papers. If we think about a stack of papers, we could think about the volume of that stack. Sure, we could have a formula, length times width times height. That would be like a box, and we could find that volume. Or another way to do this is we could look at the area or the volume of each individual slice of paper, sheet of paper, and then add all of those up. If we do that, then the width of those papers or the height of those papers are all going to be very, very small. We're going to call that dx or delta x, however you want to think about it. It's a very, very small width of that slice of paper. And what we could do is we could find the area or the volume of that slice of paper, and then we could add up all of those volumes from 1 to n. So we could have maybe n sheets of paper. We could find the volume of each sheet of paper, even though the thickness of that paper is very, very small. Add them all up, and that would give us the volume of the stack of papers. Another way to kind of think about it is with a pyramid. We could think about each layer of a pyramid. What's different about this problem is that the slice is going to look different. It's going to be a square instead of a rectangle. And as we go up the pyramid, the slices or the layers get smaller and smaller. So here we may have like 15, 20 layers. The second layer is going to be much bigger than one of the last layers. But we could do this in the same way. We could look at the thickness of each of these layers. That's going to be our dx or delta x in each case. And then we could find the volume of that little prism, of that layer. It has a small thickness, and it has a square as the area. And again, we could add up all of those, and that would give us the volume of a pyramid. And sure, we have a formula that tells us how to find the volume of a pyramid, but we are still talking about very nice shapes at this moment. We're going to move on to much weirder shapes very soon here. So with this in mind, let's look at a few different examples with this kind of idea. First, let's go back to this box or a sheet of paper or a stack of papers. Let's try to find the volume of this box with a height of 5 feet, a width of 4 feet, and a length of 3 feet. Now, we do have a formula for this, and it is very easy to use. Length times width times height would give us 3 times 4 times 5, which would give us 60 feet cubed. And that's very easy, and we should use that if this was a problem we were trying to do in real life. But we're going to try to think about this in a different sort of way. And what we're going to do is we are going to divide this box up into different slices. And I'm going to draw just one of these slices right here so we can get an idea of what it's going to look like. So there's different ways that you could have drawn the slice. You could have done this going this way as well. But we're going to just do it the other way. We have a choice. We're going to do it that way. So here's our slice, and we're going to have a lot of these different slices. The thickness of that slice is going to be dx or delta x. And if we look at this slice, we bring it out here. We could try to find the volume of this slice. We know that this is going to have dimensions of 3 and 5, the height and the length right there. And again, this little thickness of dx. So the volume of a slice is going to be 3 times 5 times delta x. We're still using that length times width times height formula, but this time just for a slice. So this is going to be 15 dx. dx is a very, very small change in x. It's a very small distance, infinitely small. So then if I want to add up all of the slices, I'm going to do that from, here's going to be x equals 0, and that would make this distance correspond to x equals 4. And for each x value in between 0 and 4, we are going to have a new slice that looks like the one that we just drew. And the more slices we have, the better approximation we're going to have for our volume. And if we have an infinite amount of slices, we're actually going to have equal to the number, or equal to the volume. So to do that, we are going to use an integral. The integral, we're going to have a slice for every x value in between 0 and 4. And we are going to have the volume of the slice at each x value. In this case, that volume is the same for every x value. That's going to give us 15. And here's where the dx comes from, the thickness of the slice. The dx means something, and in this case it means the thickness of a slice. So now we can integrate. This is a function, 15. The antiderivative is 15x. Evaluated from 0 to 4 will give us 15 times 4 minus 15 times 0, which gives us the 60 feet cubed that we knew we were going to get at the beginning. This is just a much different way to think about volumes, and this process allows us to do a lot of different things with much weirder shapes. So let's go on. Now we're going to look at the volume of a cylinder with a radius of 3 centimeters and a height of 5 centimeters. In this case, we're going to take slices, and we have a couple different options. We could look at slices horizontally, and a slice in that way would look like a circle, or would be a circle. We could also look at slices vertically, but that would not be as nice of a slice. We'd get a rectangle, but those rectangles would be different each time. That would be kind of hard to deal with. So the nice way of dealing with it is going to be with a circle or a little disc right there. The width of that disc is going to be dx, and the area of that disc is going to be pi r squared, in this case where r is that 3 centimeters. So that's going to give us pi 3 squared, which is going to give us 9 pi. Times the itty bitty dx is the volume of the slice. Now we're going to have a slice for every x value in between x equals 0 all the way to x equals 5. And maybe this is a good time to think about that we don't actually need to call this x. We could call this instead y equals 0, all the way to y equals 5 since we're going up, or maybe we could even call it h equals 0 and all the way to h equals 5 since we're talking about height. In this case, let's look at y equals 0. That looks kind of a nice thing to do. It's all the way to y equals 5. In that way, then this distance wouldn't be dx, this would be dy. It's a small change in y. That means that all of these things would be dy instead. So the area here would be pi r squared dy or pi 3 squared dy. So what we're going to do is we are going to have this volume is going to be the integral from 0 to 5. We're going to have a slice for every y value all the way from 0 to 5. We drew one of those right there. And then we are going to find the volume of a slice at y. So the one that we drew is we drew for some y value here. We drew that slice. We're going to do that for every slice in between 0 and 5. And we have a formula for that. That's going to give us pi, or 9 pi dy. And we can integrate. When we integrate this, that's going to give us 9 pi y, as 9 pi is a constant, evaluated from 0 to 5. That gives us 9 pi times 5 minus 9 pi times 0, which is going to give us 45 pi. This should be centimeters cubed. Now, what's the case for the last two examples, and the first example we saw on the first page, is that in this case the slices are all the same. And because the slices are all the same, we have nice formulas for these shapes. We know what the volume of a cylinder is. It has a nice formula. It is pi r squared h. We know what the volume of a box is. It's length times width times height. And part of that is because the slices are all the same. We're going to look at shapes where the slices are not all the same, looking at first this one on the next page. So here we're going to find the volume of the following solid whose curve can be described by the function f of x. This is a weird vase, if you want, or something like that. And you can think about the curve, if we put it on the xy axis, looks like the function f of x. This curve right here is our f of x. All right, this is circular in a kind of shape, and we're going to think about, we are going to have, for every x value from 0 to, let's call this 10 right now. For every x value between 0 and 10, we're going to find a slice. And in this case, a slice looks like a circle or a disc. Those slices look different depending on where you're at. For different x values, they're going to look different. So here's another one right there. Let's draw one more. And for each slice in between 0 and 10, we're going to draw, for each x value, we're going to draw a little slice. So let's say that we go back to our first slice here. This is going to correspond to some x value. And let's just bring out this slice so we can look at it in a little more detail here. We know that the thickness of this slice is going to be dx. It's a small change in the x direction. And we know that this is going to give us the volume of this is going to be pi r squared dx. The question is, what is r? And in this problem, the value of r is changing depending on what x value we have. The r value associated with 0 is going to be much different than the r value associated with 10, and everything in between is going to have a different value of that radius. It has a different function value is what we're really saying. And that gets us to our next point, that this radius is actually equal to the function value at x. This distance right here is exactly, if we have some x value, f of x. If we're thinking about at 10, this would be f of 10. If we're thinking about at 0, this would be f of 0. And we have everything in between as well. So the volume of a slice at some x value is going to be equal to pi r squared dx, but in this case that r is f of x. It is a formula that allows us to see how the radius is changing on each slice. So here, the volume of this shape would be equal to the integral, where we're going to look at the volume of a slice at x. And we're going to do that for every x value from 0 to 10, as that's where we're going to take slices for this shape. Then we would have that this is equal to 0 to 10 pi f of x squared dx. And since we don't actually know what this function is, we can't really go any further than this, but this would represent the volume, or a way to find the volume of that very weird shape. We would have to find the antiderivative of f squared, multiply that by pi, evaluate from 0 to 10, but we could find an answer. And this right here is what we're going to be calling a solid of revolution. And we're going to get to that on the next page or two. But we're going to start with some function. We're going to take that function and we're going to revolve it around the x-axis or the y-axis or some other line that gives us this circular kind of shape that we're going to be dealing with. So when we do this, we have this solid of revolution. Our slices are going to look like discs or washers. Discs are going to be just like little pancakes. The volume of this, we've already talked about, is going to be pi r squared dx. The washer is going to be like a disc with the center cut out. Again, we have that the thickness is dx. This time we have two radii that we have to think about. We have a big radius and we have a small radius. We'll call the one little r, we'll call the other one big R. And to find this volume, you should take a second and just reason out this formula for yourself before I even write it down. This formula would be pi big R squared minus pi little r squared, all times dx. It is the area of the big circle, the big disk, minus the volume of the small disk. The volume of the big disk minus the volume of the small disk. And this is the formulas that we are going to be using, this pi r squared dx and pi big R squared minus pi little r squared dx. That's going to give us our problems on the next page or two. So let's jump into it. Find the volume of the solid of revolution created by revolving the area bounded between y equals cube root of x and y equals x over 4 with x and y greater than or equal to 0 around the x-axis. That is a mouthful. We're going to take it step by step and try to understand what this means. First, we are going to graph these functions to understand what we're trying to deal with. We're going to graph these functions, just like we did in the last section. It might be helpful to understand what are the intersection points. We have cube root of x is equal to x over 4. We should cube both sides. It'll give us x cubed over, so we can write 4. 64x equals x cubed. Bring everything to one side. X cubed minus 64x equals 0. Factoriality x. X squared minus 64. And we get x is equal to 0 and positive negative 8. Since x and y are greater than or equal to 0, this means that we are in the first quadrant, so we're only going to consider x equal to 0 and 8. These correspond to the points. So we have our 2 points here are going to be 0, 0, and 8, 2. And let's draw the functions. We have x over 4 is going to be a line. And y equals x over 4. And cube root of x is going to look like square root of x. Connecting those points, going to go above that line. With y equals cube root of x. So that's the first step. Just got to graph those functions. And that's enough work as it is. Then it says we're going to take that area bounded in between these two functions. That's this area right here. And we are going to revolve that area around the x-axis. Take that area, revolve it around the x-axis, and that's going to give us a solid that we can find the volume of. So let's draw a picture of that volume, or that solid. We can do that by doing mirror images over the x-axis. There we go. We have this circular kind of thing. How I would describe this is like a bowl. The inside is a weird kind of, gives us a corner on the inside. It's not a very good bowl, but a bowl kind of shape there. This is a solid. It goes all the way around. And it's important to understand what this looks like in 3 dimensions. So then we want to find the volume of this solid. That's the goal here. It might help to draw the axes here. So this is the x-axis here. X equals 0 or y equals 0. And this is the y-axis. And we are revolving around that. This looks like the picture of the function that we drew a couple of pages ago. When we think about what does a slice look like, in this case, slice is going to be not a disc, but a washer. We need to find the volume of that washer for each x value in between 0 and 8. For every x value in between 0 and 8, we are going to have a little washer that we can find the volume of, and then we're going to add up all of those volumes with an integral. So let's do that now. We know that we are going to have the volume is going to be, for every x value in between 0 and 8, we are going to find the volume of a slice at x. And in that case, that's going to give us the volume of a washer, which is going to be pi big R squared minus pi little r squared dx. Our goal is to figure out what is big R and what is little r. And to do this, let's go to a new page here. Okay. I'm going to redraw our shape real quick. Redraw our slice. Our slice here we said has a thickness of dx. And when we think about the radii, our big radius is going to go from the x-axis all the way up to that green line. That green line, remember, represented the cubed root of x. So that big radius there, r, is going to be the value cubed root of x for each x value. The little radius, which we can think about from the x-axis to that red line, is going to be r is equal to, well, this corresponds to the function x over 4. This will give us x over 4. For each x value, those radii are going to change. When x is 0, those radii are going to be 0. When x is 8, those radii are both going to be 2. And it's going to be different for every x value. We have a formula that now allows us to have the radii for each x value for each washer that we have. So our volume is going to be the integral from 0 to 8. We have our x values 0 and 8. Pi big R squared minus pi little r squared dx. We could take out a pi out in front. It's a constant. And this will give us cubed root of x squared is going to be x to the 2/3 power minus x squared over 16, x over 4 squared, dx. Find the antiderivative. This is going to be 2/5. 2/3 plus 1 is 5/3. That's going to be 3/5 x to the 5/3 minus 1 over 48 x cubed evaluated from 0 to 8. which will give us 3/5 8 to the 5/3 minus 148 8 cubed minus plugging in 0, which does give us 0. And we would get our answer right there. So going back to our original drawing there, all of the information that we needed came from our original graph. We think about some x value, we could find the big radius, and we could find the small radius just by looking at our graph. Big radius again was cubed root of x, and the small radius was x over 4. The picture helps us understand what a slice is going to look like. It can help us understand what the big radius and little radius are going to be in that case. All right, we're going to do this again, but we're going to go over a different axis this time. So find the volume of the solid revolution created by the exact same area, this time around the y-axis. So we're going to redraw our shape, our area. This time we are going to revolve around the y-axis this time, taking this area, revolving it around. This shape, we can reflect our drawing over the y-axis. Is a different shape than we had before. Now it has a ice cream cone kind of shape with some kind of filling on the inside that comes to a point at the very end. And we're going to try to find a volume of this by looking at slices. In this case, a slice is going to be a washer again. And we need to think about what the volume of that washer is going to be. This time we're going to have a washer for every y value from 0 to 2. So the volume here is going to be the integral from 0 to 2, the volume of a slice at y. We know that the thickness of the slice is going to be a small change in y, dy. And we need to figure out what the radii are going to be. What is the big radius of this slice? And what is the small radius of this slice? We can get that information from the original picture if we kind of think about our slice here. The big radius corresponds to that function y equals x over 4. But this time we need to write this as x equals 4y. It has to be in terms of y. So the big radius here is going to be 4y, corresponding to that red line there. And the small radius is going to correspond to that green line, which is going to be, again, y equals cubed root of x, but we need to rewrite it in terms of y. Will give us x equals y cubed. So the small radius is going to be y cubed. So our volume is going to be the integral from 0 to 2 pi big R squared minus pi little r squared y cubed squared dy. That is the volume of a washer with the big radius and small radius. And we're going to do that for every y value in between 0 and 2. Could write this by taking the pi out in front. 16y squared minus y to the 6th dy. And we could evaluate that integral from that point on, giving us the volume of a solid created by revolving some area. Right, we're going to do this one more time with this area. But this time, we are going to revolve around the line y equals -3. So we are going to redraw this one more time. Going to revolve around the line the horizontal line y equals -3. This is going to be similar to the first problem, but it's going to be different because it's a different line that we are going around. And it's important to understand what this shape is going to look like. This time, to draw this shape, you're going to need to reflect these lines over that line y equals -3. That's like our reflection line right there. That will give us this kind of shape here. It's not as nice to draw. There we go. This is like our shape in the first problem, except there's a big hole right in the middle. This is like a this is like a bowl, or like a funnel kind of, that has a big opening at the top and it gets smaller as you go down to the bottom. If we're looking at a slice of this, we're still going to have a washer with a big radius and small radius. A thickness of dx. And we're going to have a washer for every x value in between 0 and 8. But this time the big radius and small radius are different. The big radius is going to go down to that line equals -3. And we could redraw this in the picture itself. The big radius corresponds to that distance, and the small radius corresponds to that distance, up to the red line. So this radius is going to be top minus bottom, like we did in the last section. That's going to be cubed root of x minus -3. That's our function y equals -3 at the bottom will give us cubed root of x plus 3. You can think about it's just like our first problem where the distance is cubed root of x, except we have to add 3 going from the x-axis to the line y equals -3. And little r is going to be x over 4 minus negative 3, or x over 4 plus 3. Our volume then is going to be, for every x value in between 0 and 8, we're going to have a slice. And the volume of a slice is going to be pi big R squared minus pi little r squared dx. Big R squared is going to be cubed root of x plus 3 squared, and little r is going to be x over 4 plus 3. And with that integral, we could evaluate and solve. So depending on what axis you go over, and this could be not just x, y axis, but an axis like y equals negative 3, you're going to get different radii, and the picture tells you what those radii are going to be. Without a good picture, these problems are very, very difficult to almost impossible. All right, let's do another problem, one more. Find the volume of the solid revolution created by revolving the area bounded between y equals x squared plus 3, y equals 1 minus x equals 0, x equals 2, and y equals 0 around the y-axis. So the first step is we need to graph these functions. We're going to do it one at a time. Let's start with the easy one. So y equals 0 is the x-axis, and x equals 0 is the y-axis. We have x equal 2. Draw that right there. And then the more difficult functions, we have y equals 1 minus x. That has a y-intercept of 1. And then going down to x-intercept of 1. That's our line y equals 1 minus x. And x squared plus 3 is going to be the parabola shifted up 3 units. Could draw like that, y equals x squared plus 3. So when we think about what's bounded in between all of those functions, we have this area. This area that we need to revolve around the y-axis. So if we do that, we're going to have a volume. Let's just kind of redraw this little shape here. We're going to reflect this over the y-axis. And this gives us our shape that we're looking for, and it's going to be circular in shape. We're going to find the volume of a slice, and in this case a slice is going to be a disc or a washer, and it depends on what y value we're talking about. So there's actually 3 different regions that we need to think about here. First region is going to be below the value x equals 1. Or sorry, y equals 1. The second region is going to be from y equals 3 all the way to the top. And we should say this y value at the top is going to be 7. That is 2 cubed plus 3 is 7. All the way to y equals 7. There are 3 different volumes that we're going to look at. And that's because when we're thinking about the big radius and the small radius, we're going to have 3 different values out of that. So we're going to have the integral from 0 to 1, volume of a slice at y, plus the integral from 1 to 3, volume of a slice at y, plus the integral from 3 to 7, volume of a slice at y. And we have to figure out what those volumes are going to be. Let's start with the volume from 0 to 1. If we think about a slice there, it's going to be a washer because there's a little hole in the middle. And the big radius here is going to be out to that yellow line. That's going to be 2. The small radius is going to be out to the blue line. That's going to be 1 minus x, or we can think about this is going to be x equals y minus 1. Sorry, 1 minus y. That blue line associated there. Again, our big radius here is going to be from the y-axis all the way out to that line x equals 2. And the small radius is going to be to that blue line, r. So from 0 to 1, we're going to have pi big R squared, 2 squared, minus 1 minus y squared dy. Then we're going to do this again. From 1 to 3, we're going to have a volume that's just going to be a disk. It's not even a washer. And the volume of a disk is just going to be looking at the radius itself, which is going to be 2, going out to that yellow line. So the second integral is the easiest here. This is going to be from 1 to 3, pi the radius 2 squared dy. And then finally at the end, from 3 to 7, we have washers where the big radius again corresponds to that 2, and the little radius is going to correspond to that gray line. Seen in the picture, big radius is going out to that yellow line. That's going to be 2. And the small radius is going out to that black line. That's going to be associated with that parabola, and we could write this as y minus 3 equals x squared, or x is going to be equal to square root of y minus 3. So it does have to be in terms of y. This would give us that this integral would be the integral from 3 to 7 pi big R squared 2 squared minus little r, which is square root of y minus 3 squared dy. All of those are doable integrals. We could do them each separately, have to evaluate the bounds separately. We would get the volume total. This would be a very difficult problem for this section, as we have to split it up into 3 different integrals, think about 3 separate different problems, and we have to transform everything in terms of y as well. In the next chapter, the next section, we're going to be looking at volumes. We're just going to slice everything up in a totally different way, but the process is really going to be the exact same. We're going to look at a slice, think about its volume, and then go from there.